section is entitled Taylor and Maclaurin series. Suppose we want to find the Taylor series for f of x equals e to the 2x centered at 0. We want to find the Taylor series for this. We know that any f of x is equal to the summation of the nth derivative at c times x minus c to the n over n factorial as n goes from 0 to infinity. So in our case, f of x is e to the x. So e to the x is equal to the summation as n goes from 0 to infinity. I don't have any problem with writing down n factorial. Remember, c is 0, so that's x minus 0, or x to the n. The thing is, what is the nth derivative at 0? c is 0. Well, f of x, that is the 0's derivative, is e to the 2x. The first derivative, well, the derivative of e to the any power is e to that power times the derivative of the power, which is 2. The second derivative will be 2 times the derivative of this. But we know the derivative of e to the 2x is 2 times e to the 2x times the 2 in front. Be 2 squared times e to the 2x. The third derivative, well, it'll be the derivative of this, which is 2 times e to the 2x times 2 squared. 2 times 2 squared is 2 cubed. Their fourth derivative of x is, well, it's 2 times the derivative of e to the 2x. The derivative of e to the 2x is what I just wrote, times 2 to the 3, which is 4. 2 to the 4. So we should be seeing a pattern. Now we know that the nth derivative of x, well, we know it's 2 to a power times e to the 2x. That's what all of these had in common. The first one, we can think of it as 2 to the 0, which is 1 times e to the 2x. So they all have 2 to a power times e to the 2x. And the power always happens to be the number of times they took the derivative. The fourth derivative had a 4. The third derivative, the power of 2 was 3. The second derivative, the power of 2 was 2. The first derivative, the power of 2 was understood 1. The 0th derivative, the power of 2 was 0. So the nth derivative would be that. But we just don't want the nth derivative of x. We want it at c. We want to know the nth derivative at c, which is 0. So you get 2 to the n times e to the 2 times 0. 2 times 0 is 0. You get 2 to the n times e to the 0. That e to the 0 is 1. 2 to the n times 1 is 2 to the n. 2 to the n. Since we're multiplying and the powers are the same, you have every right to multiply the bases and raise that to the nth power. And either one of these would be acceptable. My taste is to use the bottom one. So I wrote a Taylor polynomial centered at 0. I wrote a Taylor series centered at 0, which means it's an Maclaurin series centered at 0, and here it is. This is it. That's another way of writing e to the x. The big thing is to find the f, the nth derivative of f at c. Okay, let's try another one. suppose you wanted to find a Taylor series for f of x equals the cosine of x, where c is pi over 4, 45 degrees. Well, we know that f of x, cosine of x, is equal to the summation of the nth derivative at c, at pi over 4, times x take away pi over 4 to the n over n factorial. And n, if I didn't write it in the last problem, goes from 0 to infinity. The whole job is to find the nth derivative, eventually at pi over 4. Well, if f of x is equal to the cosine of x, then f prime of x is negative the sine of x, and the second derivative is, I guess, negative cosine of x, and the third derivative is sine of x, well, the fourth derivative will be cosine of x. That is, this keeps repeating. The next one is the same as the first. The derivative of cosine of x is going to be that. It's just going to keep recycling these four, repeating them. Now, what is f of pi over 4? Remember, the sine of pi over 4 and the cosine of pi over 4 is square root of 2 over 2. So the cosine of pi over 4 is square root of 2 over 2. And negative the sine of pi over 4 will just be negative the square root of 2 over 2. And the next one is negative. The second derivative at pi over 4 is negative the square root of 2 over 2. And the third derivative at pi over 4 is just sine of pi over 4, which is square root of 2 over 2. And this keeps repeating. It's positive, and then negative, and then negative, and then positive, and then positive, negative, negative, positive, and then positive, negative, negative, positive. To write it from left to right, it's positive, negative, negative, positive, and then that repeats. Positive, negative, negative, positive, repeats. Positive, negative, negative, positive, positive, negative, negative, positive, forever and ever. The first one, we might say, we can isolate. 2 negatives, 2 positives. 2 negatives, 2 positives. 2 negatives, 2 positives. 2 negatives, 2 positives, because the next one will be plus, minus, minus, plus. 2 negatives, etc. Other than the first one, 2, 2, 2, 2. It isn't actually alternating. Well, if you consider n times n plus 1 over 2, if you consider negative 1 to this, it's actually going to give you plus 1, minus 1, minus 1, plus 1, plus 1, minus 1, minus 1, plus 1, plus 1, minus, minus. It gives you what we want. Actually work that out. Make sure you're happy with that. Make sure I'm not making this stuff up. I've been known to do that. Okay, so the Fn, so this is equal to the summation, and n goes from 0 to infinity. Other than the sine, it's the square root of 2 over 2. The nth derivative at pi over 4, other than the sine, is square root of 2 over 2. And we just can't forget the sine. Like I just said, the sine is going to come from negative 1 to the n times n plus 1 over 2 times x minus pi over 4 to the n, and all of this gets divided by n factorial. The one thing I would do is factor out the constant. So let's factor out the constant. So my final answer, I would write it as the square root of 2 over 2 times the summation from 0 to infinity of negative 1 to the n times n plus 1 over 2 times x take away pi over 4 to the n over n factorial. Okay, let's try another one. This one's actually easier, much easier. In fact, it couldn't be any easier. Suppose that f of x is equal to e to the x, and you want to write a Taylor series expanded about 1. So we know that f of x is equal to the summation, and this is the formula. It then goes from 0 to infinity of the nth derivative evaluated at c, which is 1, times x minus c, c is 1, to the nth power over n factorial. I can write down most of it. I can write down the n factorial. I can write down the x minus 1 to the n. This is all correct. My whole job is to figure out what the nth derivative at 1 is. Well, f of x is e to the x. F prime of x is e to the x. The second derivative of e to the x. Remember, the derivative of e to a power is e to the power times the derivative of the power. And 1 times e to the x is e to the x. The derivative of e to the x is e to the x. So the nth derivative of x is e to the x. Well, if the nth derivative of x is e to the x, then the nth derivative at 1 would be e to the 1, which is e. That's always e. F, the nth derivative of 1 is e. Here's your answer. Like I said, my style is to factor out constants. It's e times the summation of x take away 1 to the nth power over n factorial. N goes from 0 to infinity. Then there it is. That's one other way of writing e to the x. So, if this here is e to the x, dividing both sides by e, the left side becomes e to the x minus 1. Divide the right side by e, that cancels out, and that summation is e to the x minus 1. No double summation. X minus 1 to the n over n factorial. Now, if you replace x minus 1, say, with u, so you have e to the u is the summation from n goes from infinity, 0 to infinity of u to the n over n factorial. And it's silly to have u. I mean, u is just a dummy variable. I can call it x instead. That's how you write e to the x. This is e to the x. I just centered it at the origin. I centered it at 0 because it's x. It's not x minus 1 or x minus 9. It's just x. What we did at the end was not part of the problem. The problem asked us to write e to the x, to write a Taylor polynomial centered at 1 for e to the x. let's consider the next one. Suppose you were asked to do 1 over 1 plus x to the second power. Now keep in mind, this is 1 over, keep in mind that that's just 1 plus x to the negative 2. Now, the binomial theorem doesn't work for negative numbers. So, what I would think about doing here is integrating. This time I'm pretty sure integrating will work. I add 1 to the power, I get negative 1, and then I divide by negative 1. So what I get is negative 1 over 1 plus x. But this one, I know the expansion for this. It's negative 1 over 1 minus a negative x. And to really emphasize it, that's negative. I'm factoring out the negative on the top. That's negative this. Which becomes negative, this negative, the summation of this to the nth power. Now that negative in front is the same as negative 1. But negative x is negative 1 times x, both of which have to be multiplied, raised to the nth power. Okay, just like I brought out constants from to the right of their summation sign, I can put in constants. This becomes negative 1 times negative 1 to the n times x to the n. This first negative 1, the exponent is 1. When the bases are the same, whether they're negative 1 or 101, you add the exponents. 1 plus n is usually right as n plus 1 times x to the n. And n goes from 0 to infinity because that's how geometric series go. They go from 0 to infinity. So what we have here is the integral of 1 plus x to the negative 2 dx. Now, I'd rather just write that differently. 1 plus x to the negative 2 just happens to be 1 over 1 plus x squared. This integral happens to equal the summation of a constant times x to the n. N goes from 0 to infinity. If I take the derivative of the left side, I get this back. I get 1 over 1 plus x all squared. If I take the derivative of the right side, the constant stays the same. And the derivative of x to the n is n times x to the n minus 1. There is one way of representing the answer. There is one way right there of representing the answer. Okay, suppose we try this one. Suppose we wanted to do 1 plus x squared root. Write a Taylor series for that. That is 1 plus x to the 1/2. The binomial theorem says that 1 plus x, say to their kth power, this is 1 plus kx plus k times k minus 1 x squared here has to be over 2 factorial plus k times k minus 1 times k minus 2. Notice I have 3 numbers, x cubed over 3 factorial plus k, I'm going to have 4 numbers. Here's the second number, take away 1, get a third number, take away 1 more, get the fourth number, x to the 4th over 4 factorial, etc. Our k happens to be our half. Okay? So we're going to happen to get this where k is our half. We get 1 plus kx plus k times 1 less than k, x squared over 2 factorial plus 3 numbers, a half, take away 1, take away 1 again, x cubed over 3 factorial plus a half k, then k minus 1, and then k minus 2, and k minus 3, which is negative 5 halves. There's 4 numbers, that's x to the 4th over 4 factorial plus k minus 1 minus another 1 minus another 1 minus another 1 x to the 5th over 5 factorial, etc. Now, let's see what we're getting. Let us see what we are getting. We get this. We get 1 plus our half x, and then the numerator we have 1 minus sign, so it makes it minus. Odd number in multiplication. If you have an odd number of negative numbers, you're going to get a negative. If you have an even number of negative numbers, you get a positive. Okay, be clear. And 1 times 1 is 1 times x squared. The bottom is 2 times 2, which is 2 squared, times the 2 factorial. The next numerator, it has 2 negative signs, so that's a positive. And 1 times 3, I'm going to write that as 1 times 3. And you have x cubed, and you are multiplying 2 by itself 3 times the 3 factorial that's on the bottom, minus 1 times 3 times 5 is 1 times 3 times 5, x to the 4th, and on the bottom we are multiplying 2 by itself 4 times, and then we're dividing that by 4 factorial. We are getting our pattern. The signs alternate. The next one will be, it was 1, and then 1 times 3, and then 1 times 3 times 5. It's going to be 1 times 3 times 5 times 7, x to the 4th. When the power was 2, I was raising 2 to the 2nd power. When the power of x was 3, 2 got raised to the 3rd power. When it was 4, 2 to the 4th. Whenever the power of x were, that was what we were taking the factorial of. So it'll be 2 to the 4th times 4 factorial. Except, excuse me, it should be the 5th. 2 to the 5th times 5 factorial. 2 to the 5th times 5 factorial. So this becomes, I want to break off the 1 plus a half x. But I claim everything else lives up to the formula. Well, so it's plus a summation, as n, I guess, is going from 2 to infinity, y2, because the power started at 2, and then 3, 4, 5. So there is the power, will be x to the n, and on the bottom we always have 2 to the n times the n factorial. The thing that might be a little bit troublesome is the numerator. When n was 2, the numerator was just 1. When n was 3, it was 1 times 3. When n is 4, it's 1 times 3 times 5. And when n is 5, when n was 5, it was 1, 3, 5, 7. The question is, where do you end? We know the pattern, 1, 3, 5, 7, 9, 11, 13, 15, 17. But where do you end? We keep going up by 2. So you think of doubling. If you double 5, you get 10. Take away 3, it tells you to stop at 7. If you double n, you get 8. Oh, take away 3, and then 5. If you double n, you get 6. Take away 3, tells you to end at 3. So it goes from 1, 3, 5, etc. up to 2n minus 3. And here is your answer. If you want to, you could verify whether or not the first 2 terms in front fit into our formula. That is, if n started at 1, would it include this? And there is one typo, because we didn't take into account the alternating sign. The fact that the signs alternate. So let us sneak in a -1 to the appropriate power. So it's the summation. N goes from 2 to infinity. -1 to some power. Well, when n is 2, you want the sign to be negative. When n was 3, you want the sign to be positive. Well, 2 is an even number. So if you take an even number and add 1, it'll become odd. And -1 to an odd, so when n is 2 at the beginning, the power will be 3, it's odd. -1 to the odd is negative. There's your answer. There is your answer. We use the binomial theorem. You really should know the binomial theorem for 1 plus x to a number. Now, they ask us using the table. Most textbooks have a table for the standard Taylor series. They're saying using the table, write down a Taylor series for e to the x squared over 2. Well, we know that e to the x is 1 plus x. How do we know that? Because at some point as a student, we actually did this, or you look it up on your table. It's this. That's e to the x. 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 If you want to know e to the 20th instead of x, you plug in 20. If you want to know e to that power instead of x, you plug in that number. It will be 1 1 plus, instead of x, you write x squared over 2. Plus, instead of x, you write x squared over 2. Do not forget to square it and divide it by 2 factorial. Whatever being done to these x's, you do to x squared over 2. That is, next I'm going to take x squared over 2, I'm going to triple it, divide it by 3 factorial. I'm going to raise it to the 3rd power, not triple. I'm going to raise it to the 4th power, and then divide by 4 factorial. I'm going to do that forever. And there's one way of writing down the answer. Let's see if we can use or write it in summation notation, also known as sigma notation. So let's look at this a bit more closely. We got 1 plus x squared over 2. Now, the next numerator, x squared over 2 squared, well, that's x to the 4th over 4 over 2 squared times the denominator, 2 factorial, plus x squared over 2 cubed. That gives you x to the 6th over 2 cubed times the 3 factorial, plus x squared over 2 to the 4th power, 2 times 4 is 8, over 2 to the 4th times 4 factorial. And we do that forever. Now one might ask, well, is the number 1, is the first term part of this? Well, let's see. The powers are 8, 6, 4, 2. This one should be 0. And in the end, we'll see if it's right. Then you have 4 factorial, 3 factorial, 2 factorial. I can put in 1 factorial. So the next one should be 0 factorial. Then you have 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1. The next one should be 2 to the 0. And this is 1, because x to the 0 is 1, 2 to the 0 is 1, 0 factorial is 1, 1 over 1 times 1 is 1. So the first term fits in like a glove. So this is equal to the summation as n goes to 0 to infinity. And let's do the bottom first, the denominator. You have 2 to the 4, 4 factorial. 2 to the 3, 3 factorial. It's 2 to the n times n factorial. But the numerators aren't going in order. It's not going 1, 2, 3, 4. It's even numbers. First it's 0, and then it's 2, and then it's 4, and then it's 6. And you know what? 0 is 2 times 0. 2 is 2 times 1. 2 times 2. 2 times 3. 2 times 4. In fact, the power is 2 times n. 2 times 0. When n is 0, then when n is 1, the power will be 2 times 1. And then when n is 2, it will be 2 times 2, exactly like it should be. And there it is. That's e to the x squared over 2. And we used a known series. We know that e to the x is 1 plus x squared over 2 factorial, etc. In fact, possibly an easier way to do this problem would say that it's e to the x is x to the n over 2 factorial. So instead of x, we write x squared over 2 to the nth power over 2 factorial. And then coming up here, x squared to the n is x to the 2n, and in the bottom 2 to the n is 2 to the n, and you divide by, there's a typo here, it should be saying n factorial, and you divide by n factorial, and there it is. exactly what we had over here. N goes from 0 to infinity. So you can just immediately do it. That is, go from the known series, and if they change x to something like x squared over 2, fine, that's what you do. Instead of x right there, you plug in x squared over 2 and do a little algebra. The calculus part was immediately done once you put x squared over 2 wherever x was. Then the algebra kicks in. What is the Taylor series for sine of 2x? Well, we know that the sine of x is x minus x cubed over 5 factorial plus x to the 5. That's probably wrong. Excuse me. Over 3 factorial over 5 factorial minus x to the 7 over 7 factorial, etc. That is, it's the summation as n goes from, say, 1 to infinity. Possibly I'll change it to 0. Now, the powers keep going up by 2. So I think of the 2 times table. 2, 4, 6, 8. And I notice that my powers are always 1 less than the 2 times table. So I take away 1. And the powers of x happen to be the same as the denominators, which are being factorial. So it's 2n minus 1 factorial. And there's the answer. That's the sine of x. So now the sine of 2x, well, instead of x, you just plug in 2x. N goes from 1 to infinity. Instead of x, you put 2x to the 2n minus 1 over 2n minus 1 factorial. And there it is. Problem is set to the over. Instead of x, plug in that. Okay, that completes the section on Taylor and Maclaurin series, and it actually finishes the section on infinite series.